So, what is entropy? Well, sometimes it's almost like seen as a mystical concept with chaos and disorder, but actually the answer is quite simple. It's quantum physics. So, what I want to do in this video is first go a little bit into sort of more practical sort of example of where we see entropy at work in everyday life, then talk about why entropy is actually coming from quantum physics, and then how it applies to the Earth system. So, I start my day every day with a hot cup of coffee. And so when I have my hot cup of coffee, I know what happens with time. Well, if it sits on the kitchen table, with time it will get cold. Now, we know that energy is being conserved. So in other words, well, when the coffee gets cold, the room gets slightly warmer. So that's being captured by the first law of thermodynamics, that energy remains conserved upon conversion and upon redistribution. Now, this direction that this temperature difference between the hot coffee and the cool room is being depleted, that's an expression of the second law of thermodynamics, and that says that entropy increases, which basically means that the temperature differences are being depleted. And with this cold coffee, then actually we have a state that is called thermodynamic equilibrium. This is shown here on the left. It's actually a pretty boring state. So when we look into sort of processes in the Earth system, they are actually not, often there is an assumption of local thermodynamic equilibrium, but overall, the interesting processes are actually not in equilibrium. And a good picture for that is, for example, a hot cup of coffee, or actually a boiling pot of water on a stovetop, because there we actually know what's maintaining this disequilibrium. So that means that the temperature in the pot is warmer than the surroundings. Well, what maintains this disequilibrium and that temperature difference is that it is being heated from the stove, from the hot plate below. And in other words, there is a heat flux going through the system from the hot plate to the cold kitchen. And the interesting part of the hot pot is actually also that, when the water starts boiling, actually we have motion inside the pot and there is work being done because, we accelerate, or the water is being accelerated. Eventually it's, by friction at the border of the pot, it's being depleted. And so that's a much more interesting system. So we have disequilibrium systems that perform work, and that's actually more captures the essence of the Earth, because the Earth is a process in disequilibrium, or system in disequilibrium. It receives sunlight, which we will see in a minute. It has low entropy. It emits radiation to space, that's high entropy, and somewhere in between, in the Earth system, we have all kinds of processes that perform work and dissipate this work back into heat. So that's the direction we are going to go. Now, let's look into this concept of entropy a little bit into the history. Now, maybe the good starting point is Sadi Carnot, French engineer who looked at the thermodynamics, or looked at the efficiency of steam engines. This was early 19th century. This was the time where heat engines were being invented and improved. It was the onset of the Industrial Revolution. And what he noticed is that the efficiency of the steam engine, efficiency being defined as the heat that is being put in the engine and the work that the engine is actually doing, that depends on the temperature difference. So down here I gave an expression for what's known as the Carnot efficiency, and that's depending on the temperature difference, just like the temperature difference between a hot cup of coffee and the cold kitchen. Now, from that, what we also saw in the 19th century were the formulation of the first and second law. I gave here two pictures of German scientists. One can also find British scientists who proposed these principles around the same time. So we had Hermann von Helmholtz, who formulated the first law on the conservation of energy, and Rudolf Clausius around the mid-19th century, introducing the concept of entropy, and with that basically, follows the second law. And it's a well-known expression. You may know that too. You know that a change in entropy relates to heat being added or removed to a system but also the temperature at which it's being added or removed plays a role. So we have this expression here. Then, towards the end of the century, Josiah Gibbs, an American chemist, extended thermodynamics to chemistry and chemical reactions. But actually, what I want to get more into is Ludwig Boltzmann, who we have already met in the introduction of this series, Austrian physicist who introduced the kinetic gas theory. So that the picture that a gas is made out of colliding particles, and that the temperature is basically a measure for how much kinetic energy these particles have. And with this framework, or with this theory of the kinetic gas, he introduced a statistical interpretation of entropy, also quite a well-known expression that S is equal to a Boltzmann constant times the logarithm of the possibilities over which energy can be distributed over the different molecules. And this statistical interpretation was really quite a breakthrough, because it took entropy out of the context of sort of classical thermodynamics and put a statistical basis to it, and also talks about chunks of energy being distributed over chunks of objects. This was picked up by Max Planck at the turn of the century. He applied this concept to radiation laws and was able to derive these radiation laws. So here, the energy is no longer distributed over colliding molecules, but it is distributed over electromagnetic radiation, which is something very different. I mean, we are not dealing with matter, but we're dealing with electromagnetic waves. It was very successful in the sense that it was able to derive radiation laws that before couldn't be brought together. And really, that's sort of the onset of quantum physics, if you want. The experimental proof that this is indeed the case, actually Einstein gave in 1905 with his explanation of what's called the photoelectric effect. That was a curious effect that certain objects that we now call semiconductors could produce a current, but only when there was illuminated by light with above a certain frequency. That sounds sort of all a little theoretical. The practical example these days is actually photovoltaics, which actually uses the photoelectric effect. Einstein explained it using this quantum picture of Planck, and for that explanation, actually Einstein won the Nobel Prize, and nowadays we see the importance of this effect in the form of how much photovoltaics is nowadays being used. Then it took a little bit more, 20 years, so now 100 years ago, 1925, seen as the year where quantum physics was formalized, also by works of other physicists like Max Born and so on. But also where Werner Heisenberg actually introduced the uncertainty principle, which means that you can't precisely determine the location and the momentum of a particle in the quantum picture of the world. And I think the reason why I'm mentioning it here is actually because I think that's actually the origin of the second law of thermodynamics. But, well, let's leave it at that. Then there's a lot more evolution to quantum physics. But now, so what does that actually mean for entropy, and when we bring this concept back to the Earth system? What it means is that entropy is more than just heat, because in the quantum world of things, we can distribute energy over photons. These are the carriers of electromagnetic radiation. We can distribute energy over electron levels in atoms and molecules, and we can distribute energy over vibrational and modes of motion in molecules. So that's what I show here on the left-hand side. So we can distribute energy over photons, electrons, and molecules over a certain number of states. And then we need to come back to Boltzmann and apply maximum entropy to get formulations in the classical physical way. So when we want to describe solids, liquids, and gases, and radiation fluxes, and so on, we need the scaling of maximum entropy to get to these expressions in the non-quantum world. And so what we have is basically at least three different forms of entropy. We have radiative entropy dealing with radiation, and we will see shortwave radiation is actually low radiative entropy, long-wave radiation is high radiative entropy. We have molar entropy that deals with material properties. For example, water as a liquid has a lower molar entropy than a gas because the electrons have a lot more freedom to arrange in a gas than in a liquid. And we have the classical thermal entropy that comes from classical thermodynamics. So when we apply this to the Earth system, then actually we can see why it is important to characterize these three different forms of entropy. Because what's driving the Earth system? Well, it's obvious, it's the sunlight. So solar radiation, electromagnetic waves, they were emitted at a high temperature, about 5,500 degrees centigrade. And if you remember the expression of Clausius, entropy has to do with heat or energy being a certain amount of energy being removed divided by temperature. Well, the temperature is very high, so at the Earth, at the orbit of the Earth, the solar radiation has a very low entropy. And how that materializes is that basically this low entropy solar radiation has short wavelengths. It means that the energy is distributed over fewer photons that have each a higher energy, and so that's low entropy. Then some of that is being absorbed, it's being converted. We have energy conversions on the planet, and their entropy takes different forms. When it does geochemistry, it may end up in molar entropy differences. When it heats and cools certain places, we may have thermal entropy differences. And overall, the whole system produces entropy, which means that the radiation that is being emitted to space actually has longer wavelengths. There are many more photons, each with less energy, and overall, this is a lot higher entropy. So, when we come back to the original question, what is entropy? Well, entropy comes from quantum physics. It is because in the quantum world, energy is quantized and distributed over different modes, and this can be carriers of electromagnetic radiation called photons. We can distribute it over electrons that orbit around nuclei, or we can distribute it over moving modes of motion of molecules. So three forms of entropy. Then, in order to derive expressions of classical physics, we need to assume that energy in the quantum world is distributed in the most probable way. So we assign a probability to the distribution, maximum entropy, and that's then yields expressions that we can use in classical physics. And so overall, this increase of entropy that the second law tells us that processes need to do, it doesn't just apply to heat, it applies to all processes. It applies to the whole sequence from the interior of the sun to the surface of the sun, through the radiation that travels through the space to the Earth, and all the processes that happen on Earth, including life. And well, before we get to life, we will first look in the next video on why entropy is so relevant.